Alright, so what we did in the last lecture was try to explain how the notion of normal family makes sense for a domain which includes the point at infinity, okay, and the technique as that we always follow is that you make a two-piece definition, okay. You make one definition for the domain punctured at infinity, which will be a domain in the usual plane, and then to take care of a neighborhood of infinity, what you do is that you invert the variable z to 1 by w, and instead of considering z equal to infinity, you have to consider w equal to 0. So you take you consider a neighborhood of 0, okay, which is again it's also a domain in the usual complex plane, okay. So you therefore you are able to treat the case of normality at infinity, okay. So with that we saw that both Montel's theorem and Marty's theorem hold good for domains which probably include which may include the point at infinity, okay, that is domains in the external complex plane. And of course I also told you that it is a matter of terminology, that a family being normally sequentially compact, that is sequentially compact with respect to normal convergence, that is sometimes abbreviated to simply normal family, okay. So now what we are going to do is, as I told you, we have come very close to the proof of the Picard theorems, which was the main aim of all these lectures, okay. And but before that there's something called, there's a theorem which is called as Zalcman's lemma, which we have to use, okay. And see, this has got to do with a characterization of non-normality, okay. So what we so in order to motivate this Zalcman's lemma, okay, what we are going to do is we are going to try to analyze what happens to a normal family at a point, okay. So so let me make this definition. We define normality of a family at a single point to be normality in a small neighborhood of that point, in an open in an open disk containing that point, okay. So this is just like definition of analyticity. So you see, you say a function is analytic if it's differentiable not only at a point but in a small neighborhood of that point. So in the same way, normality is also defined at a point by requiring the property in a small open disk surrounding that point, or a non-empty open set containing that point, okay. Well, of course any open set containing that point is non-empty. So the reason for this definition is that normality is a local property, okay. If you have, for example, a cover of your space which is countable, and if your domain can be covered by countably many open sets, and on each of these open sets, if your family is normal, then on the whole domain also the family will be normal, because you can use, because of countability, you can use a diagonalization argument, okay. So so normality is a local property, okay. So the first thing I'm going to start with is so I'll put the heading as motivation. Let me use a different color. Motivation for Zalcman's lemma, which is actually a characterization of non-normality. So what we will do is we make the following definition. Let script f be a family of meromorphic functions defined in a neighborhood of a point z0. Okay. Of course, this point z0 could also be the point at infinity, but let us assume that z0 is a point in the plane. The case of, you know how to treat the case at infinity. Okay. Suppose this is a family of meromorphic functions defined in a neighborhood of z0, that means it is defined in an open disk containing z0. Okay. We say the family script f is normal at z0 if it is normal in a neighborhood of z0, in open neighborhood of z0. Okay. So well, so that is the definition, and so the question is, suppose a family, and of course a family is normal on a domain if it is normal at every point. Okay. Further, family is normal on a domain if and only if it is normal at each point. So I should not say further, in fact this is a remark. So this is a remark that you can check. I mean, it just says that the notion of normality is a local property. Normality is a local property. Fine. So here is the question. The question is, I now have a family defined in a neighborhood of a point. Okay, it's a family of meromorphic functions, and it's given to me that this family is normal. Okay, and I want to analyze how the family behaves at that point. Okay, so the clue to Zalcman's lemma, or at least an understanding or motivation for Zalcman's lemma, is trying to understand this. Okay, so what we will do is so I call this as local analysis of normal family. So let script f be meromorphic in meromorphic be a family, let script f be a family of meromorphic functions on mod z minus z0 less than or equal to rho. Okay. So you see, mod z minus z0 less than or equal to rho is actually a closed set, it is a compact set. Okay. If that's provided z0 is a point in the usual complex plane. If z0 is infinity, then you have to rewrite this as a you must rewrite this as you should not use the Euclidean metric, but you have to use the spherical metric. Okay. But I am assuming for simplicity that z0 is a point in the plane. Okay, and this is a closed and bounded set. I'm taking a compact set because I can choose such a row. Certainly it's a family of meromorphic functions at the point z0, so it is defined in a neighborhood of z0. So it is defined on a small enough disk which contains z0, and if you take a smaller enough radius, then the closed disk centered at z0 of that radius will also be in the domain where the meromorphic functions are defined, where the family is defined. So I am taking without loss of generality this closed set because the reason is I want a compact set so that I can I can get uniform convergence. Whenever I talk about convergence, uniform convergence, it happens only on compact sets, it's normal convergence, and whenever I talk about uniform boundedness, it happens only on compact sets. So for everything I need a compact set. That's the reason why I am doing this. Okay, so what it means is that the family is defined on a bigger open set which contains this closed set. Okay, Now you see what we want to do is we want to really so let me draw a diagram. So here is Z0, all right, and here is this, there is this disk centered at Z0 radius rho. So this is the disk centered at Z0 radius rho, and the point is you give me a family, you give me a function small f in the family script f, okay, and what I want to really do is I want to really analyze this function in that small disk, okay. I want to analyze this function in the small disk, and how do I do it? So what I do is I have to look closer at the small disk. So what I actually do is zoom in, okay, and how do I zoom in? So it's by scaling, okay. So what I do is that I put I define g for every function f in the family. I define this g, and what is this g? This g is defined with the new variable zeta, and this is defined as f of z0 plus epsilon times zeta. I put this condition, I make this definition. So what's happening is that this is in the z plane. So the variable here is z, so this is also the complex plane, and then I have another complex plane, okay, and this is the this is the zeta plane. So the variable here is zeta, all right, and what I do is I take this unit disk, okay, I take this unit disk, this is unit disk mod zeta less than 1, okay, I take this disk, and now I am defining this function g as a function of zeta, okay, and what is g? It's actually you have just magnified the behavior of g at the value of g at zeta is the value of f at z0 plus epsilon times zeta. So what it means is that if you start with a yeah, and of course I am assuming that epsilon is less than rho, okay. So if I take this disk of radius 1 centered at the origin with the variable zeta, then if I multiply by epsilon, if I take epsilon zeta, it will become disk of radius epsilon, okay. So it will be a smaller disk like this, okay, and this will have radius epsilon, okay, and then if I add z0 to it, I am just translating it to give me a small disk of radius epsilon centered at z0. That's what this does, okay. So you're just multiplying epsilon to zeta, then you are adding z0, so that's translation by z0, okay. So basically what you're doing is that when you do this, you're actually looking at this, you're looking at this small disk centered at z0 radius epsilon, and so in principle for what values of zeta is g defined. So you'll see that g is defined for should be rho by epsilon. See, if mod zeta is less than rho by epsilon, okay, then mod epsilon zeta will be less than rho, and mod z0 plus epsilon zeta will be less than, therefore also less than rho, okay. See, mod zeta is less than rho by epsilon means that mod epsilon zeta is less than rho, okay, and what does this tell you? This tells you that the distance of epsilon zeta from the origin is at most rho, and therefore if you add z0 to epsilon zeta, the distance of z0 plus epsilon zeta to z0 is at most rho. So this is, so you see this g is defined on this disk, and you see this disk is actually see this disk is larger. See, because you see rho, the original disk centered at z0 has radius rho, alright. Now the radius has become rho by epsilon, and epsilon being smaller, rho by epsilon should be larger. If you think of epsilon to be epsilon is less than rho, so rho by epsilon is greater than 1, okay. So what you have done is, by this transformation, this disk centered at z0 radius rho, okay, if you want to study the function value of the values of the function f there, the behavior of the function f there, what you have done is you have actually zoomed it by constructing this function g. So g is a kind of zooming function, okay. It's like you have a microscope or a telescope and you have 10x zoom, 20x zoom, you see that also in cameras these days, okay, you have 5x zoom and so on. So this is some so many x zoom, and the zoom is the zooming factor is 1 by epsilon, okay. Original disk of radius rho has now become zoomed to disk of radius rho by epsilon, okay. And well, the point is that and of course rho by epsilon will be slightly bigger, okay. You will get, so this is epsilon, this thing will be rho by epsilon, and it's in this bigger disk, open disk, that the function g is defined, and studying this function g in this bigger disk is the same as studying the function f in the original disk, okay. So you know, I'll write it like this. I'll write g of zeta is equal to zoom. I'll think of it as zoom the function f centered at z0 by a magnification factor 1 by epsilon, and use the variable zeta, okay. I'll use this notation, okay. So when I say zoom f z0 1 by epsilon zeta, you are zooming the function f centered at z0, so your zooming your zoom is centered at z0, okay, and 1 by epsilon is a magnification factor, and zeta is the variable of the zoomed function, okay. Now well, the so this is how you zoom into the behavior of a function at a point, okay. Now I am given that this function I am given that this family script f is normal. Suppose I am given it is normal at z0. Suppose it's suppose I am given it's normal in this closed disk centered at z0 radius rho, which means it's actually normal in an open set which contains that closed disk, okay. Suppose that happens, and let's see what it means for us. So let me continue like this. Suppose now that you know script f is normal in mod z minus z0 less than or equal to rho, okay. By that I mean it's normal in a slightly bigger open disk, okay. Then so what does normality mean? It means actually normally sequentially compact. It's the correct notion of compactness for us when we do complex analysis, okay. So what it means is that you give me any sequence of functions in script f, I can always find a subsequence which converges normally, okay. It's normal sequential compactness. It's sequential compactness with respect to normal convergence. So given any sequence fn in script f, we can find a subsequence, let me call that as fnk, that converges normally in mod z minus z0 less than rho, okay. I can put less than or equal to, okay. In fact mod z minus z0 less than or equal to rho is actually compact, and therefore it will converge even uniformly there, okay. So it converges normally. So what happens is that you will get this subsequence fnk of z, it will go to some function fz, okay, and f is a normal limit of meromorphic functions. So you know what's going to happen, we have already seen this, a normal limit of meromorphic functions is either identically infinity or it's also a meromorphic function, it could even be analytic, okay. So then of course then as we have seen either f is identically infinity or f is meromorphic. This is something that we have seen, all right. But the point I want to do want to emphasize is that is the following issue. You see, you have these functions f and k, they are converging to f, all right, and what is happening is that now you know mind you, I have the zoomed functions, okay, I have these zoomed functions by a zooming factor epsilon less than rho. So look at the zoomed functions. So what happens is that I take g and k, which is actually the the zooming of, so g and k of zeta is the zooming of f and k with respect centered at z0 with a magnification factor 1 by epsilon, and I am using the variable zeta. Okay, and similarly I get the limit, I get a zoomed function for the limit function also. So I get g also is equal to the zoomed function of f centered at z0 magnification factor 1 by epsilon, my variable is zeta. Okay, so this is g of zeta. So I have that, and of course you know if f and k converges to f, then the zoomed functions of the f and k's, namely the g and k's, will converge to the zoom function of f, which is g, and this is just because the zooming is just a scaling followed by a translation. Okay, so after all, what is the zooming? The zooming is you multiply zeta by epsilon, and then you add z0 to it. Okay, that's just a, in fact it's actually a bilinear transformation. It's a linear fractional transformation. It's a Mobius transformation. Okay, so it's a so it will preserve all properties, convergence, everything. Okay, so you get this. Now you see, so let me write this. This is normal, normally. So here also I'll get, so this will imply that this will also converge normally. Okay, and the point I want to make is that, you see, I have assumed that the original family is normal. Okay, and we have seen, namely Marty's theorem, that normality is equivalent to the spherical derivatives being normally bounded. Okay, so if you recall, you know, Marty's theorem says that a family of meromorphic functions on a domain, the domain could even be a domain in the external complex plane, it could contain the point at infinity. Such a family is normal if and only if the spherical derivatives of those functions, the family of spherical derivatives, is normally uniformly bounded. So it should be on every compact subset of the domain, the family of spherical derivatives should have a uniform bound. Okay, so by Marty's theorem, you know that the family script f itself has a if you take the spherical derivatives, then that has a uniform bound. Okay, so let me write that down. By Marty's theorem, script f has a uniform bound. So script f hash, so when I put script f upper hash, it means the family of spherical derivatives of the functions in f. Okay, this has a uniform bound in mod z minus z0 less than or equal to rho. I have this. Okay, because mod z minus z0 less than or equal to rho is a compact set. Alright, and on a compact set I will have a uniform bound for the spherical derivatives, and that is equivalent to normality. Okay, this is something that I have. This is Marty's theorem. So so what does it mean? It means that if you take any function f in so let me not use f, let me use h, because I have already used f for the limit. If you take a h in f, then h hash, this is the spherical derivative of h, is less than m for all h. Okay, and same m. Right, so you have this, you have uniform bound. All right, and this bound applies to all members of spherical derivatives of all members of the family f, script f. So it applies also to the fn case. Okay, so in particular what you will have is you know you will have that fnk hash, the spherical derivatives. You see, these things are going to be bounded by m. This is going to happen because all these fnks are anyway in the family. Okay, but you know we have also seen this earlier. If a family of meromorphic functions converges normally to a limit function, then the spherical derivatives will also converge. Okay, taking the spherical derivative will respect convergence. Okay, so you also have from you also have from here if you want. So I need to go like this, that f and k, if I take the spherical derivatives, that will go to f hash, okay, you have this, okay, and of course, you know, if I by the same token, if I do it to the gn case, the spherical derivatives of the gn case will go to the spherical derivative of g, okay. Mind you, gn k is just fn k translated and scaled. So when you translate and scale a function, its nature does not change. So if you take a meromorphic function and translate and scale it, you will again get a meromorphic function, okay. After all, translating and scaling is not going to change the nature of singularities, okay, and if you translate and scale an analytic function, you will again get an analytic function, okay, and so on and so forth. So the g and k's are also meromorphic functions, and mind you, you have to remember that I am considering the f and k's in mod z minus z naught less than or equal to rho, but I am actually considering the g and k's in mod zeta less than rho by epsilon, okay. That is the disk, that is the zoomed disk centered at the origin where the zoomed functions are being looked at, okay. So let me write this here on mod zeta less than rho by epsilon, okay. This is there, epsilon is less than rho, right. So this is a quantity greater than 1, fine. So I have this, and I also have the same thing for these guys. I will also have g n k hash going to g hash, all right, and of course it's again normal. This is also normal, okay, and the point is that but there's an inequality coming now. See, what is g n k? G n k of zeta is by definition f n k of z naught plus epsilon zeta. This is a zoomed function. So so what is g n k hash of zeta? What is it? It's, see, it is by definition, it is supposed to be 2 times the modulus of the derivative of g n k with respect to zeta divided by 1 plus modulus of g n k of zeta the whole square. This is the definition of spherical derivative, okay, and but then this is what is the g n k dash zeta in the numerator? It's the derivative of g n k with respect to zeta. It's the derivative with respect to zeta, okay, and mind you, this formula for spherical derivative also works when zeta is a pole, okay. We have seen that, you know, by continuity, if the pole is of higher order, then the spherical derivative at the pole is 0. If the pole is a simple pole, then spherical derivative at the pole is actually 2 divided by modulus of the residue at the pole, which is something that we have seen already, okay. So there is no problem if zeta is a pole, okay, this formula works. But then, you know, if I differentiate g and k with respect to zeta, it is the same as differentiating f and k, and then you know, by the chain rule differentiating the argument of the f and k with respect to zeta, and that will bring me a multiple of epsilon. So what I will get is I will get epsilon times f n k hash of z. This is what I will get, okay, not z, in fact I have to plug in the right substitution, scaled variable z naught plus epsilon zeta. This is what I will get, okay. And but what is but the f and k's are all bounded by what? The f and k's are all bounded by m, alright. So this is bounded by epsilon m, okay. So the moral of the story is that because of your scaling, okay, see, what you must understand is that you zoomed the small disk centered at z naught radius rho to a larger disk, okay, you scaled and you got the zoomed function, but what has happened is that the bound for the spherical derivative has become smaller because it has got multiplied by this the inverse of the zooming factor. The zooming factor is 1 by epsilon, where epsilon is very small, okay. Then your bound, the bound for the zoomed function becomes much more smaller, okay. Now that is what it says. Now this is true for every nk, but you know, g n k hash converges normally to g hash, and each of the g n k's is bounded by epsilon m. Therefore, you know, g hash will also be bounded by epsilon m. So these two put together will tell you that g hash will also be bounded by epsilon m, okay. So this will happen, alright. So that is because of normal convergence, okay. So the moral of the story is that so this is what is happening. So what have we shown so far? You take a point Z0, a point where a family is normal, okay, and then you take any sequence in the family, you will get a convergent subsequence, normally convergent subsequence. You look at those functions in the subsequence, okay, and zoom them. Then the zoomed functions, their spherical derivatives become very small. And in fact, the zoomed functions, if you take the limit of the zoomed functions, the limit function will be a meromorphic function whose spherical derivative is very small. That's what it says, okay. And now you know, so this is the first step of the argument. Now what I am going to do is I am going to introduce a level of complication by doing the following thing. What you do is, instead of considering a single epsilon, you consider a sequence of epsilons going to 0. Imagine you are considering, I am using the same epsilon here for all the functions, okay, but suppose for Gn I use an epsilon n, okay, and such that the epsilon n's are going to go to 0, okay. That means I am doing ultra zooming, I am zooming into smaller and smaller and smaller and smaller neighborhoods of Z0, okay. If I do that, then what will happen is that you can guess what is going to happen. This G hash will be 0, because see G hash will the thing on the left side, Gn hash, Gnk hash, that is going to be bounded by epsilon nk m, okay, and if I take limit as nk tends to 0, epsilon nk is going to go to 0, so epsilon nk m is going to go to 0 because m is anyway a finite quantity, therefore G hash is going to go to 0. And what does it mean if G hash goes to 0? It means that G is a constant. A spherical derivative of a function cannot be 0 unless it is a constant. It can be even the constant function that is uniformly infinity, mind you, for the constant function which is uniformly infinity also the spherical derivative is 0, okay, in line with the fact that the philosophy that whenever you have a constant function the derivative of any type should be 0, okay. So the moral of the story is, this is the moral of the story. The moral of the story is that if you zoom in a family of convergent, normally convergent family of functions at a point, okay, then the limit function is going to be constant. That is the whole point, okay. So let me add that level of complication, but now there is something very nice. What is happening is that this, so let me put this in a different color here. Whatever is happening is happens in mod zeta lesser than epsilon, I am sorry, rho by I think it was rho by epsilon, okay. This was the disk where everything is happening, okay, but now you know if I make these epsilons go to 0, okay, by choosing epsilon n's which go to 0, something nice is going to happen. As epsilon n's go to 0, rho by epsilon n's go to infinity. So your disks are becoming bigger and bigger and bigger, and the beautiful thing is that any compact subset of the complex plane, the zeta plane, will be contained in a sufficiently large disk, and therefore you get a family of functions for which you can talk about normal convergence on the whole plane, okay. So this G hash will be defined on the whole plane and you will get a constant function, okay. That's the whole point, okay. So let me write this down. Now let us consider a sequence of epsilons, say epsilon n going to 0, so epsilon going to 0 plus, so they are all positive quantities, and you know let me say even I mean say even decreasing, okay. Anyway a sequence going to 0 eventually is going to be a decreasing sequence, right. strictly decreasing sequence, you can think of it as smaller and smaller neighborhoods. Okay, then what happens is that we get for so here is a funny thing, you define Gn of zeta to be, you zoom f, so you take f, you write z0 plus epsilon n zeta. Okay, this is actually the zooming of the function f centered at z0. Scaling factor is now 1 by epsilon n, and the variable I am using is zeta. Okay, and mind you, this 1 by epsilon n is going to go to infinity, because epsilon n is going to 0 plus 1 by epsilon n is going to infinity. That means I'm doing ultra zooming, at the point z0, and I'm looking at the zoom functions. All right. Now see, this is defined, as I told you, this is defined in mod zeta less than rho by epsilon n. Okay, and the point is that this goes to infinity. This goes to plus infinity as n tends to infinity, because epsilon n goes to 0, rho is a fixed quantity. Right, and note that what will happen is that g n k hash will go to g hash as before. Okay, this will be normal, but the beautiful thing is this will be normally on C, on the whole of C. That is the beautiful point. Earlier this gnk hash going to g hash was on only on this bounded domain. It was on mod zeta less than rho by epsilon. It was normal on the convergence. Gnk hash going to g hash was, it was normal convergence on this bounded domain. But now, since these epsilons are becoming smaller, these the GNs are being defined on bigger and bigger domains. Okay, that is an increasing sequence of disks, open disks centered at the origin, that will eventually cover the whole plane. So it will eventually cover any compact subset of the plane, and therefore on any compact subset of the plane I can say that this sequence is going to converge normally, because I will have to consider the sequence only beyond a certain stage. Okay, see, whenever you are looking at convergence, the first finitely, no matter how large, the first finitely many terms do not matter. Okay, so the moral of the story is that the advantage of taking smaller and smaller epsilons is that you are zooming into the point, you are zooming into the behavior of the functions at that point, but then you get a limit function which is defined on the whole plane. So you get a meromorphic function on the plane. So this G, it will be a meromorphic function on the whole plane. Okay, G will be a meromorphic function on the whole plane. All right, and the nice thing is that as I was telling you, the bound for the spherical derivatives of Gn will be what? It will be epsilon nk times m. So you will get gnk hash is bounded by epsilon nk times m. Okay, because earlier we got the bound as epsilon m for gnk. Okay, but now the epsilon is epsilon nk in this case, so I will get this. Okay, and this goes to g hash, and as k tends to infinity, and well, this goes to 0 as k tends to infinity. So the moral of the story is that g hash is 0, and this implies that g is a constant. And when I say g is a constant, mind you, g could be the constant function which is identically infinity, that is also allowed. Okay. So how do you argue that g is a constant? Mind you, g becomes g, anyway the limit function g is meromorphic on the whole plane. Okay, so it has only poles on the plane. Okay, and outside the poles it is an analytic function. Okay, but outside the poles the spherical derivative is 0 means ordinary derivative is 0. Okay, and if the ordinary derivative is 0, the function is constant. So except for these isolated set of points which are poles, everywhere else the function is constant, and those points cannot be there. You cannot have even a single pole, because if you have a pole, as the points approach the pole, the function goes, the modulus of the function values goes to infinity, How can it be constant in a deleted neighborhood of a pole? So that forces the function has to be identically constant. That's how you get G is identically constant. G is only a meromorphic function. Okay. So this is the important thing. The important thing is that if you take a normal family, so what have we proved? You take a point where a family is normal, okay, and you take any sequence in the normal family, you can find a normally convergent subsequence. If you take those sequence of functions and do zoom in at the point, you are able to construct, see the zoomed functions will converge to a constant function. That is what it says. Okay. If you look at a normally convergent family of meromorphic functions zoomed at a point, you will get only a constant function in the limit. That is what you are saying. Okay. This is the behavior of a normal family at a point. Okay. And what I want to do next is introduce another level of complication. Okay. And this next level of complication is to vary Z0 also. Okay. So instead of considering a point Z0, all this time I had fixed Z0, but now what you do is you take a sequence of points Zn which goes to Z0. Okay. And at each Zn you zoom to epsilon n for the function fn and do this process. Okay. And you will still get the same result. Okay. And the beautiful thing is that whatever you get there, okay, that behavior is good enough to characterize normal families. Okay. And the point about Zalcman's lemma is the negativity of that statement. Okay. So roughly Zalcman's lemma is a lemma that's it's actually a theorem which will explain when a family is not normal. It will give you necessary and sufficient conditions for a family to be not normal. And guess what the condition will be? The condition will be that you can do all this, but the limit function that you get G, it will be non-constant. That will be the only difference. You will get a limit function which will be a non-constant meromorphic function. So its spherical derivative will not be 0. Okay. And that is a characterization of non-normality. Okay. That is this is the motivation for Zalcman's lemma. Okay. So in my next lecture I will tell you how to instead of considering Z0, consider a sequence Zn which goes to Z0 and have the same argument. Okay. And continue with Zalcman's lemma. All right. So I will stop here.